Okay, so basically you have this kind of little apparatus. So basically one side is filled with a type of gas, so it's here nitrogen, and this side is filled with only oxygen gas. And there's this thing in the middle called a stopcock, and basically it just separates the gases from one another. Okay, this is the, I guess, the initial part of before they mix. But basically initially it's at 2 liters, 1 atm, same temperature, and then 3 liters, 2 atm. So this is basically before we combine the gases. Okay, so as we learned before, they're going to have their own independent volume and pressure. And then what happens is, in the scenario, they open the stopcock, and then basically the gases are allowed to mix. So the N2 here is going to flow to the other side and fill up this space. There's still going to be some here. And then the O2 that was here is going to move to the other side and fill up this space. Because we know that gases expand to fill their container, right? Once the barrier is gone, they expand all the way. And then the question is going to ask us, what happens to the pressure? Because here, the pressure is 1 atm, right? But it's when it's inside of only 2 liters. But what's going to happen is the N2 is going to fill up the entire container, and you're going to notice the volume is going to increase, right? So let's start with N2, because that's what the question is asking. It's asking what's the partial pressure of N2 after mixing. So let's start with what we have. Initially, P1 is 1 atm, and initially the volume is 2 liters. Okay. Now we are looking for P2, the final pressure, and that means in order to solve this, we need to figure out V2, what's the final volume. So it's pretty easy. What's the final volume? Yeah, 5, because it was at 2. So this side is 2, this side is 3. So if you open it and then it's allowed to expand, you just kind of add up the volumes together. So it'll be 5 liters.
Really hard.
Extremely hard. Yes. All right, so you've got P1, V1, P2, V2. And if you guys remember, this is Boyle's law. So P1, V1 equals P2, V2. And we are solving for P2. Okay, so I'm going to give you guys about 2-3 minutes. See if you guys can finish A and B and C. Okay, so A is for the partial pressure of nitrogen. B is the same thing, but with oxygen. And then C is the total pressure, which we learned at the end of class last time. So it's honestly not too bad once you understand what's going on. But this is a very common type of question on the AP test. And it's going to be on your exam coming up. So see if you can finish this up. And then we'll go over in about 2-3 minutes. Thanks for the affirmation. Alrighty, guys. So we got the answer up there. I'll show you guys how I plugged it in, but for part A, we're doing the numbers from nitrogen. Nitrogen's original pressure was 1, volume was 2. Final volume is when they combine, so 5 liters. So 1 times 2 divided by 5 gives you 0.4 atm for the nitrogen. Okay. Same thing for the oxygen, just have different P1 and V1. Your P1 is 2 liters times 3 liters divided by 5 will give you 1.2 atm. And then for the total pressure, you just add them up, and that's going to give you the total pressure. Okay. Remember what we learned last time? The total pressure is equal to the partial pressures of the gases. There's another type of partial pressure problem that comes up very often, and it's this right here. Okay, so you're not going to have this picture on the AP test, but let me explain what's going on. I have a picture here just so that you can see it. Okay, so this is going to be our starting situation, and this is going to be our final situation. Okay, so basically what's happening is you have a container like this, and then it's filled with water. Okay, and typically there's going to be measurements on the container. Okay, and then what happens is there's going to be a chemical reaction that produces a gas. So it looks like this reaction right here. So here we're going to have a reaction where zinc and sulfuric acid react together, and they produce these two compounds. Now, the important one is the gas that is produced. Okay, so this is going to produce H2 gas, And what's going to happen is in the reaction, the H2 gas is going to get funneled with this tube into this container. And as you guys all know, gases rise above fluids, right? If you ever farted in a bathtub, very easy way to notice it. The gas rises up, right? Almost instantly. That's the same phenomenon here, okay? You pump the H2 gas in, and then the gas rises, and it displaces the water. So the water gets pushed out of the container, and up here, the H2 gas gets trapped. And because there are measurements, what we can do is we can basically measure how much H2 gas was produced. Okay, that's the general scenario. But there's a couple things that we need to keep in mind as we're solving this problem. Okay, so let's take a look at the problem first, and then I'll explain the little intricacies that come with it. So this is our reaction that happens right here. Okay, and we said that H2 gas is produced and it ends up in this container, right? Okay, now the question tells us that 159 milliliters of wet H2 is collected over water. So I'm gonna stop right there. Okay, so what does wet H2 mean? So an interesting characteristic of water is that it auto vaporizes. So if you have water just kind of sitting there, it doesn't just perfectly stay all liquid molecules. Even if it's not boiling, some of the molecules are going to vaporize. Okay, and so if we have this container, what's going to happen is some of the water molecules, the H2O, is actually going to leave the liquid and become H2O gas, and it's going to get trapped in here with the H2. So there's going to be H2 and H2O gas inside of the container. Okay, so what H2, what that basically means is, it means that it's the pressure of the H2, so let's write this down. It's the pressure of the H2 and the pressure of the H2O gases. Okay, that's what wet H2 means. It's basically total pressure. It's the pressure of the H2 and the H2O. So when we're trapping a gas inside of this thing right here, it's called a iodometer. Okay? When it gets trapped in there, there's going to be the gas that you collected and the water that's auto-vaporizing. Okay? That's what wet H2 is. And it tells us right here that it's going to be 159 milliliters. That's the volume. Okay? It gives us a temperature, 23 degrees Celsius, and it gives us the pressure. Okay? So the total pressure is going to equal 738 torr. Okay, and the question is asking how many grams of zinc have been produced. Okay, so we're looking for grams of zinc. Okay, so a lot of things going on, but I'll show you guys how to solve it. It's honestly pretty easy. It's just ideal gas law and then some stoichiometry. All right, so let's talk about this last statement right here. It says the vapor pressure of water at 23 degrees Celsius, so the temperature that we're looking at, is 21.07 torr. What that means is the pressure of water at this temperature, the auto vaporization, is going to be 21.07 torr. Okay, so the wet H2 has a total pressure of 738. And 21.07 of it comes from the auto vaporization of the H2O molecules. All right, guys, so the pressure of just the H2, you should get 716.93 torr. Everybody good with that? Okay, it's just subtraction. Total is 738. You subtract the 21.07, and that's going to give you H2. So if we can go back to our diagram, let me just kind of show you guys, just so that you guys have another visualization of it. Inside of this container, The H2, the pressure of just the H2 gas is going to be 716. That's what we just calculated. And the pressure of the H2O is going to be 21.07 torr. That's what we had. And so the total pressure in there is going to equal 738 torr. Okay, that's pretty much what's happening. You got H2 and H2O, and those are the partial pressures, which gives you a total pressure of 738. Okay. All right, so from there, what we're going to do is, the question's asking us to find zinc, right? So we're trying to find grams of zinc, which means in order to do that, we need to figure out the information that something about H2. We need to find out moles of H2 because that's going to allow us to convert it to zinc using stoichiometry. So we have pressure, we have volume, we have temperature, and so we can calculate moles using the ideal gas law. So we're going to use PV equals nRT. So let me give you guys about 2 minutes. I know it's been a long weekend since we did this, but look back at your notes. See if you can calculate for moles, and just make sure that you convert torr into ATM before you do that. Okay, it's going to be 760. So 760 torr is 1 ATM. So take about 2-3 minutes to do that. See if you can find moles of H2 with ideal gas law. And if you feel comfortable going all the way to zinc, go ahead and do that. But at least try to get moles of H2. All right, guys, everybody good with getting the moles of H2? That part's not too bad, right? You got to convert pretty much every unit, though. So torr to ATM, milliliters to liters, Celsius to Kelvin. So this was kind of like a test of seeing if you're paying attention. You know what units of measurement to use. And then we learned about the ideal gas constant last time, the 0.0821. Okay, so you get 0.0062 moles of H2. Now, we're not done yet. Because we're not looking for moles of H2, we're trying to find grams of zinc, right? And so what we have to do is we need to do stoichiometry one last time in order to convert the moles of H2 into grams of zinc. So we're going to take our moles, so 0.0062 moles of H2. We're going to set up our fractions, and we're going to get our numbers from the balanced equation. Now, if you look, this is already balanced, so you don't need to balance it. It'll just be 1 mole of H2 for every 1 mole of zinc. And then you're going to find the molar mass of zinc and plug that in and get your final answer. Okay, so let me give you guys about a minute to solve that. See if you can get your final answer for zinc. And then we'll be all done. Alrighty, guys. Molar mass of zinc is 65.39. So just get about 0.4, 0.41, 0.405 grams of zinc. Okay, so this one's a little tricky because you got to understand the scenario, a lot of conversions, ideal gas law, and then stoichiometry after. But honestly, if you kind of don't understand it, just watch the video again, practice doing it, just brute force it, and just memorize how to do it because it'll be on your exam. Yeah. Okay, so the next part of gas laws is something called the kinetic molecular theory of gases. You can call it KMT. Okay, and basically this is where we learn about the assumptions we make about gases when we talk about them in AP Chem. Alright, so a lot of these you guys don't need to write it down because we already have these assumptions in our head. We're just kind of putting words to it. But the first assumption we make is that gases are made out of a lot of particles. So atoms, molecules, and they're constantly flying around. So just think about the air around us. There's a lot of molecules in the atmosphere around us, and they are constantly moving, and we can't really know where each individual one is going. They're just kind of bouncing around everywhere. Okay, the second, we talked about this before at the beginning of the unit. We said that the volume of the actual molecules is very small compared to the volume of the container. So if we have the room like this, most of it is empty space. The molecules are extremely small. Most of the volume of the gas is taken up by empty space. We talked about this already. Okay, the third one, the attractive and repulsive forces are negligible. So basically, they're not reacting with each other, so there's no reactions. Okay, that's some of the assumptions that we make. And because they're flying around, they have these gas molecules, they have kinetic energy. Okay, so kinetic energy is just the energy you have in motion. And when we think about our world, right, when two things in motion hit each other, they're going to lose some of that kinetic energy, right? But when we talk about gases, we're going to assume that the energy is not transferred through them. So they don't lose any kinetic energy as they bounce off different objects. Okay, and then the last one is very simple. We just use Kelvin temperature. And the Kelvin temperature is proportional to the kinetic energy. So for this last one, I do want you guys to write this down. Okay, but just keep in mind that the temperature is going to have a direct correlation with the kinetic energy of the molecules. Okay, we'll talk about that a little bit more in detail in a second. Okay, because that's what the graph down here is telling us. But the temperature is directly proportional to the kinetic energy. Okay. All right, now let's talk about kinetic energy before we talk about this this graph. But this is the formula for kinetic energy. If you take physics or took physics, it might look familiar. 1/2 mv squared. Okay. And so there are two things that are important when it comes to kinetic energy. Okay, the first is going to be the mass of the object, basically how big the object is. Okay, and then the second is the velocity. Think of this as the speed. Okay. So the amount of kinetic energy something has is dependent on the mass and the speed of the object. Easy way to think about this is, let's say there's a car. Okay, if two cars are traveling at the same speed, so you got a small car and then you got like a big truck. Please don't judge my drawings. Okay, you got a big truck. Obviously, the truck has more mass, right? And so if they're traveling at the same speed, which one has more kinetic energy? Yeah, obviously the bigger one. Okay, so that's one thing that determines kinetic energy, the mass. But let's say that the truck was moving at 1 mile per hour and the car was moving at 100 miles per hour. Which one has more kinetic energy? Yeah, obviously a small car, because the velocity makes up for the mass. So kinetic energy, easy way to think about it is, do you want to get hit by that object? And how can we manipulate that? Okay, so that's kinetic energy. Now this applies to gases as well. So let's look at two different gases, and we're going to talk about them before we get into this chart. Okay, so let's look at a very small gas. The smallest one we have is H2. If you look at H2, H2 is 2 grams per mole. Okay, that's the molar mass. Okay, now let's look at one that's a lot bigger. If we look at xenon, xenon is 131.29 grams per mole. So significantly bigger than H2, right? All right, and so this is where the kinetic energy equation comes into play. H2 is very small. Xenon is very big relative to one another. Okay, but let's say that we have them in a room where they're at the same temperature. So let's do STP. Let's say they're both at STP 273 Kelvin. Okay, so if they are both at 273 Kelvin, that means they both need to have the same kinetic energy. Okay, they need the same kinetic energy. Okay, however, if you look at it, we said that H2 is really small, right? So how can we get H2 to the same temperature? What do we need to do to H2, basically? Yeah, it needs more velocity. It needs to move a lot faster. Okay, and so that's the concept behind kinetic molecular theory. Basically, if we want to TLDR it, the smaller the gases, so small gases move faster at the same temperature. Yeah, they need to compensate for their smaller mass. And this is the key thing for KMT. Okay, if the smaller the gas, the faster they need to move to be at the same temperature. Okay, so the gases around us, there's a lot of different gases. Like nitrogen gas, this is the most common one, 28 grams per mole. There's oxygen, O2 gas, which is 32 grams per mole, right? If we have a room like this, which is pretty much a homogeneous temperature, right? Like, let's say this is around 70 degrees Celsius. Which gas is moving faster in this room, nitrogen or oxygen? Nitrogen, yeah. The smaller gases is moving faster. The oxygen, the bigger gases, move slower, because temperature is not about the speed. Temperature is about the kinetic energy. Okay, so that's the key thing to note about this. Smaller gases move faster at the same temperature, and vice versa. Bigger gases move slower. Okay. Any questions about that concept? Okay, it all has to do with kinetic energy. Okay, just remember, temperature is about kinetic energy, not the speed. The speed is going to change based on what gas we're looking at. Okay, now that leads us into this diagram right here. Basically, if you're going to see this, you might see this on the AP test. It's not going to be on our exam, but you see this in your textbook and whatnot. But this chart basically tells you at different temperatures what percentage of the gases are moving at a certain speed. So let me zoom in a little bit for you guys, just so we can see it a little better. If you have it on your Chromebook, it's probably better. Okay, let's look at the black line first. The black line is at the lowest temperature. So we're going to look at our lowest temperature first, 273 Kelvin. Okay, now if you look at this curve, it tells you basically the percentage of molecules that are at a certain speed. Okay, so if you look at it, the highest percentage of molecules are a little less than 400 meters per second. You guys all see that? So most of the molecules at 273 are at about less than 400 meters per second. But let's look at the next line right here, 373. If we heat up the gas, do you guys notice how the highest percentage shifts over to the right, right? So basically what this chart is telling you is that as you increase the temperature, okay, you increase the percentage of molecules that move faster, that are moving faster. Okay. And then you see with blue, it shifts over to the right again. Okay. Now, the key thing to note here is that it's not all of the molecules. Not all of the molecules are going to move faster. If you guys notice, regardless of what temperature you're at, you're still going to have molecules that are moving very, very slowly, right? That's one of the ways these types of questions try to trick you. They ask you, hey, are all the molecules moving faster? No, it's not all of them. Just a higher percentage of them are going to be moving faster. When we work with gases, we're talking about percentages and ratios. Just know the higher the temperature, the higher percentage of molecules that are moving faster. Okay? And that's what this chart is telling you. All right, we're going to look at one more graph that often comes up when it comes to KMT. We're going to skip that. It's what we already talked about, but we're going to look at some of the molecules now. So in the previous graph, we were comparing different temperatures. Here we are comparing different gases. So if you guys take a look, we got a bunch of different gases, and they all have different molar masses, so different sizes. Now, if you notice, I'll just tell you guys right now, O2 is the biggest and H2 is the smallest. So just take a look at this graph for just a minute. I'm going to just shut up for a bit, and I want you guys to just kind of draw some conclusions. You guys don't need to write it down, but just look at the different gases and how the mass changes their curves. Just take a look at it and just kind of digest it for like a minute or so. All right, so let's just kind of put together what you guys should have seen. But if you take a look at this graph, you got different gases, right? And it's what we talked about before. The bigger the gas, the slower they're going to move. So if you take a look at O2, the majority of the heaviest gas are going to have a very low relative speed, right? So this is what we talked about earlier. The bigger the gas, the lower the kinetic energy, okay, and the speed that comes with it. Actually, not kinetic energy, sorry, just speed. Lower the speed. Okay, but if you look at the smallest gas, which is H2, if you look at it, the average speed is a lot higher, right? The smaller the gas, the higher the speed. Okay. So that's the first observation you should have noticed. It's what we just talked about when I explained KMT to you. The other thing that you should notice is that the bigger gases, they don't get to the top speeds that the smaller gases do, right? And it makes sense because if we look at the kinetic molecular theory, okay, if the heavier gases were getting to those speeds, it'll actually end up increasing the temperature of the gas. And so that's pretty much what this chart is telling you, okay? You might have to interpret this for the AP test. It's not going to be on our exam, but just be familiar with what this graph is telling you and just be able to draw some conclusions based on it, okay? All right, so that's KMT. There's no real questions on this. It actually kind of leads into the next thing, but any questions on this final graph? Okay. All right, let's get into the second last topic, and this is actually one of my favorites. It's called diffusion and effusion, okay? Diffusion and effusion. So let's start with diffusion, okay? Diffusion is very simple. It's in this right here. Diffusion is where gases, if you have a barrier blocking them from moving, diffusion is when if you remove that barrier, the gases spread out across the container. So good example is if I farted right now, right, then the gases would diffuse to all the corners of the classroom, right? The barrier would be my body, right? You remove a certain part of my body and you let the gases out, it will spread the gases across the classroom. Okay, effusion is even funnier because it's the escape of a gas through a small opening. Okay, so we got gases trapped in the container and then a small hole emerges. And then the gases are able to move across the small hole and spread out across the container. I'm not going to go into too much detail, but you can kind of guess where I'm getting at, right? But the gases are going to effuse through the small opening, the unspecified small opening, and spread out across the classroom. Okay? That's effusion. That's the difference between the two. Now, on the AP test, what the questions you'll be asked about diffusion and effusion are basically the rate. Basically, how quickly does a gas diffuse and effuse? Okay, and it's actually very simple. It has to do with KMT. I'll just give you the concept and then I'll explain it in a second. So the rate of, I'll just write D and E just to represent diffusion and effusion. Okay, is proportional to the molar mass. Okay, so it's going to depend on the molar mass. Okay. Now let's talk about why. If we remember the kinetic energy equation, right? We talked about how smaller gases move faster, right? Smaller gases move faster, which means that smaller molar masses, so lower molar masses, so smaller gases are going to have a higher rate of diffusion and effusion. Okay, because they're moving faster. So when you fart, there are different gases in there. Okay, let's pick methane, 16 grams per mole. Methane moves a lot faster than sulfur, which is 64 grams per mole. Okay, so methane, the flammable part of your fart, will actually spread out faster across the room than sulfur, which is the smelly part of your fart. So the flammability of the gas will diffuse faster than the smell. Okay, and so that's kind of what the rate of diffusion and effusion is. Basically, the smaller it is, the faster it moves, so the faster it's going to diffuse and effuse. Okay, and that's pretty much it. You will have a question like this on your exam. When we do our review, you'll see an example, but basically it's going to give you two gases and be like, which one diffuses and effuses faster? That's pretty much what the types of questions will be. And you just look at the molar mass. Yes?
So the higher the molar mass, the slower.
All right, so last topic, gas Stoich, and it gives you this information right here. If you allow 15 grams of this compound right here, we're going to just label it 15 grams, okay, is allowed to react with 2 liters of chlorine gas, and the pressure is 1.5 atm, 21 degrees Celsius. How many grams of this product can you produce? Okay, and we actually need to look for the limiting reagents.
So this is the main part.
Okay. So the first, or doing the calculations for this is very simple. It's just regular stoichiometry, right? You take 15 grams and you convert it. The new stuff is the one with the chlorine gas. So I'm going to go over that part with you. If you feel confident doing this, you can just ignore me and just solve the problem on your own. But I'm going to show you how to do the gas part, which is new. Okay, so let's talk about chlorine. So it tells you the volume. The volume of chlorine is 2 liters. The pressure is 1.5 atm. And then the temperature is 21 degrees Celsius. Okay, and so what we're going to do, if you look, we have P, V, and T. We're probably going to be looking for moles of chlorine gas. Okay, so we're going to use PV equals nRT, the ideal gas law, to calculate for moles of chlorine. Okay. All right, guys. So I got the final answer up there for you guys. You guys can obviously finish your work. Double check, but the NaClO2 will be your limiting reagent, and so the actual amount you can make is 11.18. It's the smallest number. Okay, so last question of the unit, and we'll take our break after this. I'm just gonna leave this for you guys. Now, this question right here requires you to know your polyatomic ions, because you have to write the balanced equation. I know. So if you have not, please write or please memorize your polyatomic ions. I will give you guys about 5 minutes to do the whole thing, and in about a minute or two, I will put up the balanced equation for you so you can double check, make sure your memory is serving you right with the polyatomics. If not, just make sure you memorize it because you will need to know them for the test, okay? So get started on 520, see if you could write the balanced equation, but I'll put them up in about a minute or so, okay? All right, guys, so if you have questions, please let me know. But again, the hardest part was finding the two equations and then balancing them, and then you just do regular Stoich, find moles of CO2, add them up, and then you're going to get your final moles of CO2. Okay, so this problem has a lab setup, and it kind of explains what's going on. So basically, what's happening is you have ethanol right here, and you are dehydrating it. So it's a type of reaction, but basically what you're doing is you're separating it into C2H4 and H2O gas. Okay, if you guys take a look, they're both gases. All right, so if you take a look at the problem, I'm going to zoom in a little just so we can write a little bit more. But if you take a look at the problem, it says that you have 0.2 grams of ethanol. It's a liquid right now, though. And then they heat it up until all the liquid turns into gas. So 0.2 grams of liquid turns into 0.2 grams of gas. Okay? And then it runs the reaction. So this reaction takes place. And as the reaction takes place, the volume of the gas that's collected is going to be 0.0854 liters. The pressure is 0.822 atm. And then the temperature is 305 Kelvin. Okay, so we're just pulling information out. Now, if you take a look, this reaction produces two different gases, right? So you can identify from that the pressure of this container is the total pressure. So the total pressure is 0.822 atm. That's going to be both the C2H4 and H2O gases pressures combined. Okay, and then if you didn't catch it, they kind of tell you directly that the H2O gas, the vapor pressure of the gas, the pressure of just the H2O is going to be 35.7 torr. Okay, so that's all the information that is in the problem. Any questions about that? Just pulling the info out. Okay, hopefully that part's not too bad. And then the question is asking, find the moles of C2H4. So how many moles of this gas were produced? So it's first saying that was actually produced in the experiment. So we are finding the actual yield right now. Now, the actual yield is based on the experimental data, so we're going to have to use this stuff right here. Okay, so in order to find the moles of C2H4, we're going to have to use these gas laws. So let's start with the pressure, because we have volume, we have temperature, and if we have pressure, we can use the ideal gas law, PV equals nRT, in order to solve for the moles. Okay, so first thing you want to do is you want to take a look at the pressure of H2O, and you want to turn that into ATM, because we have it in torr, right? So 35.7 divided by 760 is going to give us our ATM for the vapor pressure of water. That's going to give you 0.04, I'm going to round it up to 7 ATM. And that's the vapor pressure of water. Okay, so the water vapor pressure right here is 0.047 ATM. The total pressure is 0.822. So we're going to take 0.822 and then subtract the vapor pressure of water. Okay, that's going to give us 0.775, and that remaining gas is obviously going to be the only gas we have left, so 0.775 ATM of C2H4. Now that we have P, we have V, we have T, we can solve for the moles, and we can plug that into our ideal gas law. Okay, I'll give you guys a minute to do that on your own, and this would be a good time to ask any questions if you guys have any. All right, guys, so ideal gas law, you should get 0.0026 moles of C2H4. Everybody good with that? Okay, now, this is the actual yield from the experiment because this is based on your experimental data. Part 2 is where you're going to use this right here, the 2 grams of C2H5OH, and then you find moles of C2H4 using stoichiometry, and that'll give you your theoretical yield. Okay. Now we're not going to do it this class. We'll finish this up next class, but just based on what we know about actual and theoretical, which number do you think will be bigger, part 1 or part 2's number? 2. 2 should be a bigger number because this is the theoretical yield. It's always going to be greater than the actual. Okay. So we'll stop right there, and then when we come back to class next time, we will complete this problem, and then we'll keep reviewing.